Hello and welcome to the Daily Space. Today is May 30th. As far as I know, it's Wednesday, although with this holiday week here in the United States, it feels kind of like a Tuesday. As always, I am here to bring you all that's new in astronomy and space science. For those of you who are new, I am Dr. Pamela. I am the Director of Technology at the Astronomical Society of the Pacific. The show is part of CosmoQuest, and I'd encourage any of you who have a few extra brain cells to click on over to CosmoQuest.org and help us map out other worlds while you learn about the science behind everything we study. We have a particular call out right now for data on Mars and Mercury. So if you could help us map these worlds and find the scientifically interesting features, we'd really appreciate it. Now, today's news is, it's a slow news week. Next week is going to be the meeting of the American Astronomical Society out in Denver, Colorado, and many scientists are holding their big news for the big press releases that will be happening at that conference. For now, we are trolling through the archives, AstroPH, looking for the latest papers with what we think is perhaps the most interesting science you'd like to hear. Today's big story is actually more of a photo story. The Very Large Telescope down at Paranal in Chile has released this amazing new image of the star-forming regions around the Tarantula Nebula. Now, as you look at this image, you may not just right off the bat see a tarantula, but were you to look through a small telescope from somewhere down in the southern hemisphere, this region where we see a spiky bit here, a spiky bit here, and these two nebula that curve around, this looks very disturbingly like a tarantula staring at you through the eyepiece. If any of you have a chance to go down to the southern hemisphere, I strongly recommend that you, visit an observatory and look through a telescope. This particular nebula is located in the Large Magellanic Cloud. This is one of the nearest medium-sized galaxies to our own Milky Way. It was long thought that the Large and Small Magellanic Clouds were in orbit around our Milky Way, but new results from the past few years have shown they're actually moving at escape velocities, and it's only this special moment in cosmic history that allows us to see these irregular galaxies as close to our own. Now, this particular region of star formation, the tarantula itself is about 160,000 light years away and is 1,000 light years across. So this is a massive nebula. Within this nebula, we have a variety of different systems. Shown here in yellow, we have Hodge 301. This is a somewhat older system. It's a few million years old, and it's believed that more than 40 supernovae have gone off in this one cluster of stars. Located not too far away in this image, we have the home of supernova 1987A. This is perhaps one of the best observed recent supernova. When it occurred, we had the Hubble Space Telescope. We didn't quite have it yet. When it occurred, we were in the process of building the Hubble Space Telescope. And once it was done being constructed and launched into outer space, this nebula had expanded to the point that we were able to make amazing observations of its figure 8 structure as it slowly began to expand across the years. We're going to continue watching this supernova remnant as it evolves over time and gives us new insights into, how supernova shock waves interact with the surrounding gas and dust in their regions of the universe. Now, not everything is seen in such picturesque glory. Sometimes science, it looks more like a target for a dartboard. This is an ULMA image that has now become quite famous of a variety of gaps in a dusk ring around a young star. Now, trying to understand exactly how these dusk rings form has been a topic of much investigation. In a paper accepted into the Astrophysical Journal, scientists from Poland have run more than 100 simulations trying to narrow down what exactly influences how planets form and how they migrate through the dusk disk. In this particular study, these researchers have looked to see what factors, including the surface density at the surface of the gap, both on the inner part of the gap and the outer part of the gap, how does that affect the planet's accretion? How does it slow it down as it migrates through the disk? And what they find is it's this surface density of the gas disk at the edge of the gap in the disk that most affects a planet's migration. If that is a particularly large surface density of material, the planet is going to accrete that material, it's going to migrate inwards. As that density, as that surface density in the gap decreases, migration will slow. So these are the kinds of factors that allow planets to form hundreds of astronomical units away from a star and then migrate inwards as they accrete material from this disk. Now, continuing our theme of young planets and young stars, here we have a study that was led by Rishi Padel and researchers at the University of Delaware. This is a multi-institutional and multi-international study. Using the Canada-France-Hawaii telescope, as well as a variety of other instruments, they studied a young flare star. This is a brown dwarf star. So this is an object that is less than 80 times the mass of Jupiter. It flared up to 48 times its normal brightness during flares that were observed by the Kepler Space Telescope. This is what's called an M7 brown dwarf, and it's only about 1 million years old. In looking at it, they're looking at an object that's only 480 light years away. And what they found is this particular, roughly million-year-old brown dwarf. This is an object that is burning a special kind of hydrogen called tritium in its core. While observing this star, they observed periodic flares. This particular graph here shows the relative flux of the star over time. Here time is measured in, this would be seconds of time. Now, I'm actually looking at this. So this is the Julian date minus, so this is seconds of time. Here we have two different flare events where the maximum brightness of the flare actually goes off the top of the graph. What we are learning is stars like this. Again, this is a star that is less than 80 times the mass of Jupiter. It was able, during one of these super flares, one of these two gray dotted line events, to give off 10 to the 38 ergs of energy. To give you a sense of how much energy this is, our sun gives off 10 to the 33 ergs per second of energy. This star is normally only 3/100ths the luminosity of our sun. So this was a massive flare during which it gave off 1,000 times the energy our sun gives off, 10,000 times the energy our sun gives off per second. So this is a lesson that big energy can come in small packages, small angry packages. This kind of flare activity is why when we look at these systems, we see disks around them that may be capable of forming very tiny planets. But these are planets that probably, won't initially support life because they've undergone this amazing irradiation from, these small angry stars. This kind of behavior is observed in many different kinds of small stars, both these brown dwarfs as well as red dwarfs. Even our own sun, when it was a young star, in this case a T Tauri star, it underwent its own flares. Its flare period was much shorter, however, and likely ended before, well, our planet had cooled enough to, well, resemble anything like the kind of planet we live on today. So that was it for today's news. As I said, next week we will have news coming to us from the American Astronomical Society meeting out in Denver, Colorado. Many scientists are sitting on their biggest results, waiting to announce them there at press releases. I sadly will not be attending that meeting, but will be watching what's going on remotely. So stay tuned for more news, and this week we will be bringing you still the daily news every day here at the Daily Space, and we're going to be looking through the AstroPH archives at the latest papers being published to find you information about all the things we are discovering about the universe we all share. So if any of you have any questions, please hit me up in the chat. Once again, I am Dr. Pamela Gay, and the Daily Space is brought to you by CosmoQuest. Here at CosmoQuest.org, we offer you opportunities to learn and do science. We have a particular need for help mapping out Mars and Mercury at the moment. So if you can use some of your spare time to help us map out these worlds, we'd greatly appreciate it. If you like what you see, please give us a follow. Follows are free. The show is sustained by you. Every subscription and bit really helps. We are part of the Astronomical Society of the Pacific, a 501c3 nonprofit. So I am now going to find where I hid the window with your questions and the chat. So thank you. I want to give a big shout out to my mods. I can't tell you how deeply pleasing it has been recently to go to start the show and see that, well, things are already set up with the correct titles and everything else. You guys really make my life much easier. I see the question, are the salaries of astronomers in the U.S. large? And I can't help but laugh. So I make 30% of what I would make if I worked in the commercial sector with the exact same title I have right now. So no, they're not large. You can actually look up typical salaries. Everything is listed at the Chronicles. It's the Chronicle of Academia, so I think it's chronicle.org. You can look up normal salaries for faculty and researchers at academic institutions in the United States. No, we don't earn a lot of money. We earn a solid lower middle class income, and are able to increase it over time, but it's nothing exciting. Okay, that was a very random question. So Peter is asking, I don't know what an herb is, but I like the idea of getting 10 million of anything a week. Coffee. I need more coffee. Will podcast for coffee? Is that a thing? So what do you mean, Bill, by are these other positions readily available? I don't know. Larry, heavy hydrogen with 2 neutrons in its center is just one of the many isotopes that exists in the centers of stars, and you can get, for very short periods of time, burning of this Very happy to burn. In this case, I mean fusion. You can get nuclear fusion of this heavy hydrogen for short periods of time in brown dwarf stars. Brown dwarf stars will cease burning when they run out of that, and in some cases when they run out of deuterium. Unlike their red dwarf cousins, these won't be stars for very long. Okay, so Mr. Tom Harden is saying, I've been a graphic designer for over 20 years and always been interested in astronomy. So, there's lots of ways for graphical artists to get involved in our field. Throughout this show, I actually showed, this time I only had one artist's rendition. I often, during episodes of this issue, use graphical artists' representations of different systems and artwork by illustrators that is created to help us get a better understanding of what systems look like. We have a part-time graphical artist on our own staff at CosmoQuest who helps us do everything from layouts of educational materials to illustrations to help us explain everything that's going on. So you can find a role as a graphical artist in astronomy and space science. And honestly, there's probably as many or more openings for graphical artists as there are for actual astronomers. We are currently producing more people with PhDs in astronomy than we're producing jobs for people with PhDs in astronomy. So I have to admit, I've reached the point of only encouraging people to get astronomy degrees if they, as a human being, will feel incomplete if they don't study this topic and fight as hard as they can to get one of those rare and elusive jobs. There are lots of jobs in astronomy for engineers, for computer scientists, for artists, for people in almost every different career. So take your passion and your training and apply it to science, and find happiness that way. So high altitude Shrenkov, I'm not actually sure what you're referring to. So Paranar, it's not so much that they act like the surface tension to pull things in as much as they frictionally change the orbit of the planet. As the friction lessens, you don't have the same drag on the planet to drag it in to more interior orbits. So you burn deuterium after you burn the tritium. So you first burn hydrogen with 2 neutrons, and then you burn it first with 3 neutrons, and then you burn it with 2 neutrons. I'm having one of those days where I'm screwing up my particle physics. So yes, the license plate for the brown dwarf is CFHT BD Tau 4. So there is your license plate number. So it's not that the smaller stars are more likely to produce larger or more frequent flares. It's that it's kind of remarkable just how massive these flares are, how tiny the object is. All young stars go through an angry toddler period. This is just part of stars coming into their own and starting up stable nuclear reactions in their core. How long it takes them to stabilize out varies with the size of the star. We find that stars like our sun go through a much briefer angry flare star period than these young tiny stars do. So it's just a matter of proportion. With red dwarfs, you can get a couple billion years of flare star activity. So looking to see questions. CFHT BD Tau 4. Let me type that in to the chat. So here is the license plate of this particular star. And I can actually put in a link to the paper. So here is the particular paper I've been reading. So do we have any other questions out there? So Gira Hick asks, what do astrophysical observations show? Do you think the neutrino is a real particle? Yes, we can actually detect neutrinos, and we can detect them in multiple different flavors. There was a really cool paper recently that was able to directly detect neutrinos produced through heavy bombardments of particles at CERN, which is a particle accelerator that spans the France-Switzerland border. They were producing neutrinos there, and these neutrinos traveled all the way to a detector in Italy. And over this great of a distance, they were able to see the ratios between how many of the neutrinos were released had converted over into a different kind of neutrino. So we not only have detected neutrinos, we've detected neutrinos changing their identity by converting some of their velocity to mass or some of their mass to velocity, depending on exactly which of the transitions we've been detecting. It's cool just how far things have advanced. When I first started graduate school, we didn't even know if neutrinos had mass at all, or if they traveled at the speed of light and were another massless particle. So cosmology is part of astronomy. Astronomy is an overarching term that essentially refers to everything involving stars and beyond. So astronomy includes how solar systems form, how stars and gas build up to form galaxies, and these galaxies in turn combine to shape out the large-scale structure of our universe. Now, within astronomy, we have stellar astronomy, we have extragalactic astronomy, we have cosmology. These are all different parts of astronomy. And this is why you can find papers on all these different topics in journals with names like the Astrophysical Journal or the Astronomical Journal. So Bill is asking, basic question, I guess. I was reading lately that one way to determine the size of a star, at least in early years, was to see how long it took to be occluded by the moon. So that does require a very fast measurement, and that also requires the object to be close enough that it could potentially be seen as more than a point source. I don't know if we've actually managed to do that with anything. I just don't actually know. So what happens is, as the moon passes in front of a star, we see star, less star, no star. And we can use the rate at which the moon is moving across the sky relative to the star's motion to get at very accurately how many arc seconds across, how much angular size that star takes up. If we know how close the star is from parallax measurements, this is when we look at the star's position relative to distant background quasars and galaxies. How does its position move relative to these background galaxies as our planet goes from one side of its orbit to the other? That change in apparent position gives us the distance. The same way, if you hold your thumb up and switch which eye you're looking through, you'll see your eye jump. Not your eye, you'll see your thumb jump relative to background objects. If you work out the maths of triangles, this allows you to figure out the distance to your thumb. We can use the same idea to measure the distance to stars by combining that parallax measurement with how long it takes the moon to occult a star, this will give us, if the star is close enough to be more than a point source, and I don't know if we've made this measurement, that could give us the size of the star. Now, while I don't know if that kind of a measurement's ever been made, I do know that we've used this technique to measure the size of asteroids. In fact, what we've done is we've seen asteroids also pass in front of distant stars, and by putting different observers at different places on the surface of the planet, so they each have a different perspective on the asteroid, we can map out the shape of an asteroid by looking to see for each of the observers how long that asteroid was able to block out a background star. This is one of the cooler kinds of observations that astronomers do, and we often bring together whole sets of amateur astronomers to help us out in making these kinds of measurements. So looking through more of the chat, I see Gira is asking a question. Do you think the Copenhagen physical model can explain all the experiments, or it's time to change something? So I think here you're referring to the Copenhagen model of particle physics or quantum mechanics, which basically says that you can't detect both a particle's particle nature and its wave nature simultaneously. There's been some really tantalizing experiments that actually demonstrate a particle's wave and particle nature simultaneously, but I'm not sure if it's just that one aspect of particle physics, because at different points in the particle's passage it goes from wave to particle. There's still a lot of debate on those particular experiments. They're kind of awesome. They're actually reproducible in your own room if you have a laser and wires. But I think this falls into the category of things that my particular training allows me to say are tantalizing, and I leave it to specialists in the field to say it's time to throw away Copenhagen or not. I missed a question from High Altitude Shrenkoff. I've heard we've managed to resolve the disk of a star outside the solar system. Yeah, we've done this several times using interferometry. We've resolved Betelgeuse. I believe we've also resolved one or some of the stars in the Alpha Centauri system. This is hard. We don't do it often, and it requires combining multiple infrared telescopes to make these kinds of measurements. But yeah, we've been doing this, I want to say for at least 10 years, maybe longer. So Israel is asking, random question, if there was more stuff in the route of Pluto's orbit, would it then be considered a dwarf planet? So yes, if we had a belt of objects at Mercury's orbit, it would probably be considered whatever we deemed the nature of the objects in that belt. The current definition of planet that is out there, put out by the International Astronomical Union, isn't necessarily the best of definitions. I personally think that we either need to upgrade it to add a geophysical component, or we need to accept that anything that has been pulled into hydrostatic equilibrium, this means anything that's a sphere and orbits a star, any star, I don't care if it's the sun, should be called a planet. So let's bring back Ceres, let's bring back Pluto, or let's just completely rewrite the definition and add more geophysics to it. I don't care which, I just want a better definition. Thank you so much for sharing. Yes, I found out earlier today that I'm going to be inducted into the Podcasters Hall of Fame. I think that makes me an old lady of podcasting, but I'm super proud that this is going to happen, and now I just need to dye it to fit into a dress I already own. So thank you. Yeah, I'm an observational astronomer. Give me photons and I'm happy to count them for you. Um, I do, Zuriel, try and call them worlds. It's definitely what I try and do. I've been here for about half an hour, and Dr. Matthew Richardson is sitting patiently waiting to take over this channel. So I'm going to kick things over to him. Thank you, everyone who has followed and subscribed today. I want to give a special thanks to Hiptacular Raptor for gifting subs to Biff 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 and to High Altitude Shrankoff. And now the EH Cosmic Rays. We are giving all the high altitude particle subs today. Thank you, Under Wraps, for the follow. Thank you, Astro Helge and Biff Biff Biff, for the bits and the follow. You guys, and thank you, Hiptacular Raptor, for the gifts to Tom Van Scooter and Skeptic Psy. Let's get all the rocket icons, Master Player 301, all the rocket icons, everyone out there in the chat. You guys are amazing. I just love seeing comets flash through our screen. Hiptacular Raptor, as always, you are a spectacular community member. All the rockets should be launching out there in the chat. You're fabulous. Thank you to Mr. Tom Harbin's subscription. And Mr. Tom Harbin, get your rockets out. Once again, I'm Dr. Pamela Gay. I'm the director of CosmoQuest. I invite you to join us in mapping out other worlds. We have a particular need for maps of Mars and Mercury right now, so if you have a moment, click on over to CosmoQuest.org and help us map out our solar system. This production is part of CosmoQuest, and I will be back tomorrow to bring you more of the daily space at 1 p.m. Eastern, 6 p.m. London, and that is 10 a.m. Pacific. We are part of the Astronomical Society of the Pacific, a 501c3 dedicated to putting science in your brain. CosmoQuest.x filtered, or CosmoQuest X here on Twitch, features collaborators from all across our project. Matthew is part of the Planetary Science Institute, and Annie, who you see here on Sundays, comes to us from Youngstown State University. Please give us a follow and catch all the science we are here to bring you day after day. We are supported by your subscriptions, and every bit really helps. So thank you so much for all of you out there watching, and stay tuned as I click on over to hand this channel off to Dr. Matthew Richardson, who's bringing you Astro Office Hours. Thanks a lot, and wherever you are in the world, have a fabulous morning, evening, and afternoon. Bye-bye.